So rate of change, how fast is something changing? In this case, it's going to be a ball that was thrown into the air. This number right here, 90, is actually its initial velocity. It was thrown at 90 feet per second. This is gravity pulling it back down. And this means it was released when it was 4 feet from the ground. Okay, then for a few questions. Part A, find the velocity when t equals 1. So velocity comes from the first derivative. So if this is in feet, then when you take the derivative, that's going to be velocity. So the derivative will be, just use the power rule, so that's going to be negative 32t plus 90. And then substitute in a 1. So negative 32 times 1 plus 90, which is 58. So this is 58. I better make sure. Negative 32, assuming I can type it, okay, is 58. And the units on this would be feet per second. Now, like I said, that number right there is its initial velocity. So when the person let go of the ball, it was going at 90 feet per second. As it goes up, gravity is going to be pulling it back down or slowing it down. So it slowed down after 1 second, and now it's going 58 feet per second. Part B, find the acceleration. When t equals 1. So if the original function gives you a distance, then its derivative will be the velocity, and the derivative of the derivative, or the second derivative, that will give you acceleration. So this is how fast it's going, and this is it holding a steady velocity, or is it speeding up, or is it slowing down? So that's acceleration. So we need the derivative of the derivative. So the second derivative is going to be, the derivative of this will be negative 32 plus 0. Negative 32 is the answer. Because there is no 1 to plug in, it's always negative 32. And the units would be in feet per second. And it's changing negative 32 feet per second every second. So its velocity over time it's actually slowing down. You throw something up into the air, and gravity is going to slow it down until eventually gravity takes over and brings it back to the ground. Obviously, you knew that part. Anyway, with this, you can write it as feet per second, or the faster way to write it, or the more common way to write it, is feet per second squared. So these two mean the same thing. Then for part C, when is the velocity equal to 0? So if you have some object that is going to go up and it's thrown at 90 feet per second, it's going to be going up, and the velocity is going to be positive. Eventually, gravity is going to take over. It slows it down until at this moment, the velocity is 0. And then gravity is going to start bringing it back to Earth. So it's going to be going slow at first, and then speed up and speed up and speed up until it hits the ground. So what we're looking for is this point right here. When is the velocity equal to 0? So we already have the velocity function right here. Then just set it equal to 0. Or in other words, how long is it going to take until it gets to its highest point? So you could just add 32t to both sides and then divide by 32 and 90 divided by 32, that would be 2.813 seconds. Now I just want to see if I got it right. Let me graph this. Negative 16x squared plus 90x plus 4. And for the window, I don't need any negatives. So 0 to, let's see, I got the answer 2.8, so I don't really need that going to 10. It could go to, say, 5. And then this would be the height. How far up would it go? 20 feet in the air? 50 feet in the air? Let's try 50. Oh, 50 wasn't enough. And it looks like 5 is not big enough because I can't see this part of the graph. What I'm going to do now is trace the graph and see it's 130 feet in the air. Wow, much higher than I thought. So let me have this part go 0 to 10, and then how about 150 feet? Okay, now I can see it. And then I wanted to test this answer, 2.8, that's when it's supposed to be right at the top. So trace and put 2.813, and that should be the top of the path. Yes, that's correct. All right, so that's number 1. On to number 2, something slightly different. Suppose that you have something like a basketball or a balloon. Basketball is a little bit better because basketballs are perfectly round. I think of balloons as sort of egg shape. Anyway, let's say it's a perfectly, so right there I took care of it. It's not egg shape, it's a sphere. So it's perfectly round. And this is the volume. So then find dV dr when r equals 1 foot and explain what that means. So the derivative is with respect to r. So we're basically saying this is the independent variable. So the derivative with respect to r. So the constant 4/3 and the constant pi can just stay there. Then take the derivative of r cubed, which will be 3r squared. And then I could get my trusty red pen and have these 3's cancel each other out. Then substitute in a 1. So it would be 4 pi times 1 squared. So that's 4 pi. How much is 4 pi's? 4 pi is 12.566. 12.566. Now explain what that means. So this is saying how much does the volume change as the radius changes. So imagine you have this ball, it's really small, and you start blowing it up, pumping it up, pump up the basketball, and it's going to get bigger and bigger and bigger and bigger, and so it's getting bigger. Well, how much is it getting bigger? So its volume, so V is for volume, its volume is changing by this much as the radius changes. And this is all when the radius is equal to 1 foot. So volume is increasing by 12.566. Volume would be in cubic feet. For every 1 foot that the radius increases. So if the sphere was this big and the radius increased by a foot, then the volume would increase by 12.566 cubic feet. All right, then on to number 3. So the horizontal distance an object traveled is given by this function. Horizontal distance means that the object is going like this. Okay, that part seems obvious. But because some of these coefficients are positive and some of these are negative, what that's going to do is mean that the object could turn around and come back. And it's possible that it could even turn around and go the other direction. Now it would really go in a line, but if I drew it that way, it went this direction and then went this direction and then went this direction, then you can't really see it. So I have to draw it like this. So it could go forwards, backwards, forwards. Depending on the function, if it was like a trig function, it could go forwards and backwards and forwards and backwards and forwards and backwards and forwards and backwards, like one of those Roombas. Okay, then on to part A. Find the velocity when t equals 2 seconds. So velocity means the first derivative. So the derivative here will be 9. Oh, I put x's. Sorry, let's call it x. That's okay, it's fixed. So just use x as the variable. So 9x squared minus 10x minus 6. And then substitute a 2. So that'll be 9 times 2 squared minus 10 times 2 minus 6. How much is that? So it's going to be 9 times 4 is 36 minus 20 minus 6. So that would be 36 minus 26, that's 10. So with this being a positive, that means it's going in the positive direction. So usually when things are going left and right, we call going to the right the positive direction. And then when it's going to the left, that would be if this turned out to be a negative. So right positive, left negative. And if it was going up and down, then up would be positive, down would be negative. And then this is velocity, so its units would be in feet per second. Then for question B, when is the object at rest? So if it's going to go forward and then backward, then right there is when it would be at rest. Because it's at that point right there, it's not going forward and it's not going backwards. So it's taking just a fraction of a moment to turn itself around and then go the other way. So this also means that the velocity is equal to 0. So we already have the velocity function right here, then set it equal to 0. And we now need to solve for x. That's a good time to pull out the old quadratic formula. So it's going to go x equals negative b plus or minus the square root b gets squared minus 4 times the a times the c. And it's all divided by 2 times a. So this part right there, that's going to be 10. And then how much is in the square root? That's 100. This is 36 times 6. So inside the square root there's 100 because you square a negative and that's a positive. This is also going to be a negative times negative, so that's positive. So plus 4 times 9 times 6. That's going to be the square root of 316. And then divided by 18. So then it's going to be the 10. You know what, I should put parentheses. 10 plus the square root of 316 divided by 18. So that would be when x equals 1.543 seconds. And then do the quadratic formula when this is minus the square root. And then this is negative time, and unfortunately we can't go back in time. So we're not going to use the negative time, we're only going to use the positive time. All right, then on to part C. So this was example 3, and then for part C. When is it going in the positive direction? So, like I was saying, this thing can go forwards, backwards, and forwards, and backwards and forwards. When is it going forward? Well, with this one, when t equals 2 seconds, I've found out that it's going forward. With this one, 1.53 seconds, that's when it's at rest. So, basically, on a timeline, this would be 0, and then let time go on. And I found out that at 1.543 seconds, that's when it's at rest. And at 2 seconds, so all of this is time down here. And at 2 seconds, the velocity was equal to 10 feet per second. So it seems like over here, with a positive velocity, this is going forward. What about over here, between 0 and 1.53? So what I should do is pick a number in between. I'll just pick the number 1. And then substitute that into the derivative. So what's the derivative if I substitute a 1? So that would be 9, and then it was x squared minus 10 times x minus 6. So this would be 9 minus 16. And then that's a negative. So in here, the velocity, or at this moment, the velocity is negative 7 feet per second. So it seems that this object started off, it was going backwards. After about 1.5 seconds, it turned itself around, and then it's going forward. So for answering this question, the positive direction would be from 1.53 on forever. Because when we did the quadratic formula, we found this answer and the negative answer, and we're not using the negative time answer. So this is the only time when it turned itself around. So that means that this to the right is when it's the positive direction. So then my answer would be from 1.543 to forever. So I don't know how long this is going to run, for 2 minutes or 20 years, but from 1.53 seconds on, that's when it's going in the positive direction. And then for part D, find acceleration. So at t equals 2 seconds, its velocity was 10 feet per second. But is it speeding up or slowing down, or is it holding a constant velocity? acceleration will tell us. So we have that the first derivative was 9x squared minus 10x minus 6. The first derivative is velocity. The second derivative is acceleration. So take the derivative of the derivative. This will be 18x minus 10. And then substitute in the 2. I should have said x equals 2. Oh, it's okay. Substitute in a 2. So that will be 18 times 2 minus 10. So that is 36 minus 10. So that would be 26 feet per second or feet per second squared. So at this moment, it's going to 10 feet per second and it's speeding up pretty quickly. And that is the end of the section.